Let us discuss X-ray diffraction. You might have heard of this X-ray diffraction in your course. So let us discuss some important points in this X-ray diffraction. So X-rays, what are X-rays? As you know, X-rays are electromagnetic radiations with some wavelength, and that wavelength will be in the range of zero point 0.1 nanometer. Okay, around that 0.1 nanometer of range, order of wavelength. Okay, and when these X-rays, so we already told that these X-rays are electromagnetic radiations, and this electromagnetic radiation of this much of wavelength passed through crystals. Okay, these X-rays are passed through crystal, and then it will diffract and forms a particular diffraction pattern. Okay, so we are having X-rays. These are electromagnetic radiations with 0.1 nanometer of order of wavelength. And when these electromagnetic radiations pass through crystal, it will diffract, and that will form certain uh, pattern, and that is nothing but the diffraction pattern. Okay, and these diffraction patterns we can observe, and in this pattern, okay, when you observe that pattern formed after diffraction when these X-rays are passed through crystal, we can observe that a central spot surrounded by many other spots. Okay, so what we can observe, we can observe a central spot, central bright spot, along with many other spots surrounded by that of that central bright spot. Okay, and these spots are arranged in a regular manner. They are not irregular, or they are not random fashionably arranged, but they are regular. Okay, we are getting that pattern as a regular pattern. And the experiment was this experiment, that is the passing of these X-rays through crystal and observing that diffraction pattern, that was first performed by Frederick and Knipping, okay, with the instruction of the German physicist Lau. Okay, so what we are doing here, we are just passing X-rays through crystal, and we'll get some diffraction pattern. So let's say this is your crystal, and we are sending some X-rays from an X-ray source here. Okay, let's say this is your X-ray source, and we are sending some X-rays through this crystal, and when it's passed through the crystal, we can observe at the output, we can observe some particular pattern. In that pattern, the central one will be very bright, and surrounding with this central one, we will be having some different other bright other spots which will be less bright than the central one, but they are having some orderly arrangement. They are not irregular, or it is not randomly arranged, but some pattern which are orderly arranged, or they are in ordered or regular manner. Okay, that we can observe. So these X-rays after diffraction, I didn't show that. So you can see after diffraction we'll get this kind of a pattern. Okay. Okay, now let us consider the another explanation that is given by W.L. Bragg. Now, according to W.L. Bragg, these diffraction patterns produced by that X-rays which are passed through crystal, those patterns, okay, those spots. So these spots produced due to the reflection of some of the incident X-rays from various set of parallel crystal planes. Okay, so according to W.L. Bragg, he is explaining how these spots are produced after those diffraction that we just explained. So according to him, These spots are produced due to the reflection of, okay, reflection of some X-rays, some incident X-rays from different planes of the crystals. Okay, so if you consider a complete crystal, so the complete crystal will contains many planes in that crystal, and from that planes, if these X-rays are reflecting, if these X-rays are reflecting, and because of that reflection these patterns are forming. Okay, that is the uh, explanation of W.L. Bragg for this kind of spots formation due to this diffraction, or when we pass X-rays through crystals. So that is his idea. Okay, so it is because of the reflection of planes of crystals, different planes inside the crystal, and and those planes which contains large number of atoms. So all these large number of atoms will be considered as source of this reflection. Okay, so because of all those atoms which will be interacting with this incident X-rays, so all those atoms will be reflecting all those X-rays in some particular angle. So then that reflected X-rays can interact, and they will form these kind of patterns. Okay, that is the explanation given by W.L. Bragg, and this particular idea can be explained with the help of this figure, and this is known as Bragg's law. Okay, so when you consider the incident wave, incident radiations or incident X-rays. So we have X-ray. Let us consider a ray of X-ray. Let's say this is P, and this is an atom at position A, and this is P. Okay, so PA is the incident X-ray, and which is so atom A in the direction of AR. Okay, so that is reflected in the direction of AR. So this is AR. So this is the incident X-ray that is in the direction of PA, and which is reflected in the direction AR, as you can see from here. Okay, so that is reflected in the direction of AR. We are having an atom here. Okay, at this position. And similarly, if you consider another X-ray, which is QB. So this is Q and this is atom B, and that is another X-ray which is coming in this direction and which is reflected from that B and in the direction BS. So this is S in the direction BS. So we are considering two X-rays. One is from P to A and reflected in the direction A to R, or we can say PA, and PA is the incident X-ray, and AR is the direction of the reflected X-ray. And another X-ray with which is having the direction from Q to B and from B that is reflected in the direction BS. Okay, so let us consider like this. And what are these lines? These lines are planes: plane 1, plane 2, plane 3. These are planes of the crystal. So when you consider crystal, there are a lot of planes inside that crystal, and from those lines, from those planes, these X-rays will be reflected, and these reflected X-rays interact, and that will form the pattern. So let us consider that kind of interference or interaction between these X-rays, and then we can say these two reflected rays that will be in phase. Okay, that will be in phase, or it can be out of phase, depending on the path difference. So depending on this path difference, these X-rays will be in phase or out of phase. Why we have to talk about this in phase and out of phase? Because when they are in phase, they will interfere constructively. When they are out of phase, then they will interfere destructively. So for constructive interference, which means to get a high intensity. So for constructive interference, that is for high intensity spot, the path difference has to be integral multiple of wavelength. That is the condition for constructive interference. So the path difference, whatever you are considering two X-rays in this case, those X-rays should have a path difference of n lambda, that is the integral multiple of wavelength. N is the integer value, and here n is the integer value, and that has to be multiplied with l, this lambda. Okay, so n times lambda, this has to be the wavelength, the path difference between those X-rays, those two X-rays. Then only those X-rays will constructively interfere. And for the path difference, how we can define from this figure, you can see this is the first X-ray. So it is traveling from here and it is reaching at this point A, then it is reflecting back. And when you consider the second X-ray, which is also passing the same distance, when it reaches at this point, when it reaches at this point, okay. So let us consider up to this. Okay, so up to this it is equal to PA. Up to this it is equal to PA. Whatever remaining, that is the path difference. So I will use some other color here so that you can understand that. So you see, up to this part, they are having they covered same distance, both X-rays covered same distance. And in this path also, they have covered same distance, right? So there is no path difference. But when you consider this side, these two sides, then there is path difference. So the path difference between these two X-rays is whatever distance we are having from this point. Let us consider that as this as C, okay, C, and this as B, B and D. Okay, so this is D. Okay, so what is path difference here? Path difference is CB plus CD. That is the additional path for the second X-ray. Okay, and this additional path that is taken by this second X-ray, that should be an integer multiple of, or integral multiple of, wavelength in order to get the constructive interference. And if it is half integral multiple, then it will become destructive interference. That condition, I hope you know that. So now let us move on. So we can say this path difference CB plus CB plus BD, that has to be n lambda for constructive interference. And from this figure again, you can see what is CB. What is CB? So before that, I will say about this theta. This theta is the, as you can see, this theta is the glazing angle. That is the angle of that X-ray, I mean, between the X-ray and that plane. Angle of X-ray, angle between X-ray and that plane of crystal, that is called as glazing angle, and that is theta. And if this is theta, okay, and that is reflecting from that point A in this direction, then this also will become theta. Okay, because you know the angle of incidence will be equal to angle of refraction, or angle of reflection. This will become I, this will become R. So this two will be equal in this case. Okay, so theta will be same. So this is theta, this is also theta, and from these two we can consider this line, this line extended up to this C, and this line extended up to this D. Then this will also will be theta. These two angles also will become theta. Okay. So then if you consider now if you consider what will be CB, what will be CB? CB, this one, this distance. So CB will be this is this is right angle triangle. You can see the here. right? So CB is, let us consider this distance, that is the distance between the planes, that is D, that is interplanar distance. This is called as interplanar distance. So what is interplanar distance? Interplanar distance means the distance between each planes in the crystal. Okay. So that distance is D. So which means this central, this one which is D. Okay. And this part is CB. So the sine theta will be opposite side by hypotenuse. Okay, of that angle theta. So opposite side is CB by hypotenuse is D. So CB by D, from that figure CB by D will be sine theta, or we can say CB is equal to D sine theta. That is what we have written here, D sine theta. CB will become D sine theta, and that will be same as CD. CB will be equal to CD, and that will be equal to D sine theta. Why? Because this length you can consider, they are having same, they are same. So CB equal to CBD, CB equal to okay, this one should be BD. CB equal to BD, and that will be equal to D sine theta. Both are D sine theta. So now what will be this equation? Because we are adding this CB and BD here. So CB plus BD will become 2 times this quantity. That is 2D sine theta. Now we can write n lambda equal to 2D sine theta. That is the condition for the constructive interference or bright spot. So if you are getting a bright spot on the screen, then this should be the condition, n lambda equal to 2D sine theta. Okay, so under this condition, we will be getting that bright spot. So what is this n? N we call it as order. This is the order of reflection. Order of reflection, you can see here. N stands for order of reflection. And theta, what is theta? Theta is the angle between incident ray or incident X-ray and the planes of reflection. And D is the interplanar spacing or interplanar distance. Okay. So when you are having this condition, this is satisfied by the incoming X-rays, then we can get that bright spot. Otherwise, that will be having some different kind of interference, something destructive interference, then the intensity will be less. Okay, so here if you consider two planes and if you consider X-rays coming in this angle, so and all the X-rays, okay, this X-ray also coming in this angle, so and they are reflecting back from here and they are interfering, so that may not give you a bright spot. It depends on theta, value of theta. So it, when you consider n lambda, so for example, if you are considering the first one, first plane, then if you consider that first maximum, for the first maximum, so n equal to 1, for the case n equal to 1, so in that case this will be lambda equal to 2d sine theta. And for example, if your lambda is equal to 800, then 2d sine theta has to be that value. I'm just, for example, 100. I'm just giving some number. Okay, that is not the exact wavelength. So if lambda equal to some 100, then 2d sine theta has to be 100. Then only you will get that bright spot. Okay, that is this condition. And this condition is the Bragg's law, n lambda equal to 2d sine theta. And for first maximum, that is the first bright spot, for that n equal to 1, that is the order of that reflection, that has to be 1 for first maximum, and that sine theta 1 will become lambda by 2d. For second maximum, that is order of order will become 2, second maximum, for second maximum sine theta 2 will become 2 times, now n is 2, so 2 lambda by 2d, that is nothing but lambda by d. So that is the condition for second maximum. and we can go for the say third maximum, fourth maximum, etc. So all those things that we can consider, and the intensity of uh, the pattern, or the spot that is formed after that reflections, those intensities goes decreasing as the order of spectrum increases. When the order of the spectrum increases, the intensity will be reduced. That you can see from here. Here it is lambda by 2d, but when it comes here, it is lambda by d only. Okay. So if it is order is going to increase, then the intensity also will be uh, reduced. That you keep in mind. Here it is only sine theta. Okay, this is only sine theta that is going to decrease anyway. So here the intensity will be decreased when the order of the spectrum increases. Okay, so a combined scattering of X-rays from planes, that can be considered as a reflection. So what Bragg did, if you are considering all those atoms, or all those planes, and in these planes there are number of atoms. Okay, this is only two dimension. Okay, so in three dimension you will be having something like this, some plane like this for inside that crystal, and there will be number of atoms in this plane. Okay, with some ordered arrangement. I'm just showing that randomly. So all these atoms will become a scattering center. So when an X-ray comes, hit, and it will scatter, and the next X-ray comes and hit, it will scatter, and all these atoms will become a scattering center from that plane. Okay, crystal plane, and all together that will form as a reflected wave. Okay, so that what we have explained here, a combined scattering of X-rays from planes, that can be considered as a reflection from these planes. Okay, so because of this reason, Bragg scattering is also known as Bragg reflection, and the planes are known as Bragg planes. These crystal planes are called as Bragg planes. Okay, and at some angle of incidence, this you can see when you consider at some angles, not all in all angles, but in some angles, and if you are having some kind of angle of incidence, then this reflected, this is not restricted, so this reflected ray constructively interfere. Okay, and then that will form high intense spot. We already discussed these points, and similarly in some other angles, some other theta, for some other theta, these reflected waves will be uh, destructively interfere. Okay, and that will form dark band, or it will not form that bright spot. The intensity will be less. Okay, that is the reason why we are getting that kind of a pattern after those reflection. Okay, so this is the Bragg's law, and now we have to look into this Bragg's law further to understand what exactly the principle behind this. So let us move on, and let us consider the Bragg's spectrometer now. Okay, so this Bragg spectrometer, I will show it a diagram. Let me see, yeah, this one. So you can see this is the Bragg spectrometer to study the crystal. Okay, so this Bragg spectrometer, which consists of different parts, as we can see from the figure. So the X-rays from an X-ray tube were allowed to pass through the slit S1 and S2. Okay, this is the X-ray source. Okay, so from here, from this, I think, oh, not this one. I'm plain loss method, not this one. I think I have misplaced that figure. Let me see whether it is. Yeah, this one. This is Bragg's X-ray spectrometer. So now we can see this is the okay. This is the source, X-ray source, X-ray source, and the X-rays from that source passed through two slits, S1 and S2. You can see here. These are the slits. These are the slits S1 and S2. These are slits. So those X-rays are passed through that slits S1 and S2 to obtain a narrow beam, very narrow beam, which is then allowed to strike a single crystal. Okay, so these X-rays which are passing through these S1 and S2 slits to get a very narrow beam, and that narrow beam of X-ray which is passing through, and that is just that is interacting with this crystal. Okay, this D stands for this crystal that is in the sample that we are using. So that those X-rays are going and hitting on that single crystal mounted on that table, turntable. You can see here, and the crystal is rotated by means of the turntable so as to increase the glazing angle at which the X-rays are incident at the exposed face of the crystal. Okay, so once you have this kind of arrangement, then you have to turn um, you have to rotate that, and then that will produce different angle. As you can see, this is your crystal position first initially. So if you consider this as your incident X-ray, okay, and this angle, if you consider, you can consider in this one side, okay. So this angle, if you are rotating again, so I'm just showing it in 2 dimensions, okay. So, or I can show it like this. So it will be like this. If it is coming and hitting, so this is your angle theta, and if you rotate this crystal a little bit, and that crystal position is now something like this, but your incident ray is in the same direction. Okay, the source is fixed here. Source is fixed, so the incident X-rays will be having same direction. So that is coming in this direction, same direction, but it will be having some different kind of theta now. Okay, theta is changed. Okay, so when you rotate that crystal, by rotation of crystal, you can change that theta angle of incidence. You can change. Okay, and in here in this X-ray spectrometer, okay, in this X-ray spectrometer we are considering that rotation through the turntable. You just rotate this turntable, and so that this D crystal will be rotated, and the angle you can change, angle of incident can be changed. Okay, so the crystal is rotated by means of that turntable, and we'll increase the glazing angle at which the X-rays are incident at the exposed face of the crystal. And the photographic plate or an ionization chamber is used to measure the intensity of the reflected rays that you can see from here. You can directly use a photographic plate so that these X-rays will come After that reflection, those X-rays will come and hit on that photographic plate, and those which are having high intensity, you can see a bright spot, and those who are having low intensity will be having very small or less bright spot. And so that is one method. You can use a photographic film, or you can also use an ionization chamber. Why ionization chamber? If that X-rays are passing through that ionization chamber like this, you can see that will produce some current, some ions and electrons that you can see. You know this ionization chamber, how it will work. So when that radiation comes, it will produce some ions inside this ionization chamber, and that will produce some current. And depending on how much current that produced, we can measure how much radiation is there. So that we can say this much of intensity will be there. We can distinguish that bright and dark spots. Okay. So the angles for which reflection intensities are maximum, that give the value of theta by using the equation L lambda equal to 2d sine theta. Okay, that we already discussed. So just you consider uh, one particular angle where you will be getting maximum intensity, which means that there is this constructive interference is happening, which means it is obeying at that point, at that angle, it is obeying this condition, and put that angle in this equation for theta and calculate. You know what is lambda, you know what is n if it is the uh, first order or the bright spot, highest intensity, then n will become 1, this n will be 1. So then your lambda will become 2d sine theta. Now you know theta. Theta is the that angle that you are sending your X-rays. So now you know what is theta. You know what is lambda. That is your pump wavelength, the X-ray wavelength. So then you can find out what is d. That is the interplanar distance between interplanar distance of that crystal. Okay, that you can find out. So that is the method that we'll use here. And obviously for n equal to 1 we will be getting this condition. For n equal to 2 we will be getting 2 lambda equal to 2d sine theta. Okay, and so on. For 3 third order, this is 3d 3 lambda equal to 2d sine theta, and so on. So we can find out for different angles, we can find out what will be the d, the interplanar distance of that particular crystal. Okay. So now if you consider that values, as you can see from this relation, sine theta, this will be in an order. Okay, sine it is considered sine theta. Okay, this one also I put sine theta 2, sine theta 3, etc., because the angle also will be different in that particular condition. So sine theta 1, if you consider sine theta 1 is to sine theta 2 is to sine theta 3, these values of this sine of angles, if you consider. Okay, and that will be in the order 1 is to 2 is to 3, 1 is to 2 is to 3. Okay, that is how you can get that. If you divide this, you can take that directly from here. Let us consider this as sine theta 1. So lambda equal to 2d sine theta 1, then 2 lambda equal to 2d sine theta 2, 3 lambda equal to 2d sine theta 3. So if you take sine theta 1 by sine theta 2 from here, then we will be getting 2d 2d will get cancelled, then we'll get 1 by 2. And if you take sine theta 2 by sine theta 3, then we'll be getting 2 by 3, and so on. So then we get this relation 1 is to 2 is to 3. Okay, I hope you understood that. Let us put that here. For example, lambda equal to 2d sine theta 1. So, and then 2 lambda equal to 2d sine theta 2. If you divide these two, then we'll be getting 1 by 2 equal to sine theta 1 by sine theta 2. or we can say sine theta 1, sine theta 2 equal to 2 sine times sine theta 1. So that is the relation. That is, which means sine theta 1 is to sine theta 2. If you take, that is 1 is to 2. When sine theta 1 is 1, sine theta 2 will be double of that. And similarly, if you do the same exercise for third one, then you will be getting sine theta 2 will be equal to 3 times sine theta 1, or it will become it will become 3 times sine theta 1 and 2 times sine theta 2. Okay, so that's how it will come. And hence, by measuring the glazing angles theta, different angles at which that reflection occurs at different orders, we can determine the interplanar spacing by knowing the X-ray wavelength. Now let us consider as an example, let us consider the first order reflection maxima that is occurred at some 5.9 degree. This is corresponding to palladium. Okay, and this is 5.9 degree, 8.4 degree and 5.2 degree first order maxima. For this, these are corresponding to the planes 100, 110, and then we are having 111. These are the planes. Also, these planes will produce this at these angles 5.9 degree, 8.4 degree, and 5.2 degree maxima that will be produced at these angles. So, which means that we can have the condition and lambda equal to 2d sine theta, 2d sine theta in this, for this case. So, first one will be, this one is the first order. Okay, this one will be the first order maxima. So these are for different planes. Okay, so these are the first order maxima for different planes. So that we'll be having n lambda equal to 2d sine theta, then lambda n equal to 1. So lambda will become 2d sine theta, or d will become what is d? D is lambda by 2 sine theta. So you substitute those value of theta here, and lambda you know, and once you substitute that, then we will be getting what is the interplanar distance. Now if you calculate that, then we can get that, for example, if you take the ratios of that interplanar distance, then d100 is to d110 is to d111, d111. Okay, so if you take this ratio, then we can write this as 1 by sine theta 1 is to 1 by sine theta 2 is to 1 by sine theta 3. Okay, this is, so this is corresponding different angles. Okay, so this is theta 1, theta 2, theta 3, and so on. If you take like that, then that will be these planes. If you take interplanar distance, then it will be like this. So d100 d is to d110 d is to d111. That will be 1 by sine theta 1, 1 by sine theta 2, 1 by sine theta. So the ionization current or the intensity, you can consider intensity or ionization current. So that is, if you consider ionization current on this y-axis, ionization current versus the incident angle theta, then we will be getting something like this. This will be produced, and then here will be high intensity, then again here will be some high intensity, and so on. Something like this. Okay, so this is your different values of you can see here it is. So these are n equal to 1, n equal to 2, and this is n equal to 3. Okay, so order you can see this is let us this is a 1, this is a 2, and this is a 3. Okay, now if you take the ratios, these ratios, if you take these ratios, what will be the values? Then the values you can easily get by substituting those sign. Theta 1 is 5.9, this is 2, 1 by sine 8.4 degrees, okay, all are in degrees, 1 by sine 5.2 degrees. So then that will be, if you take that values, then 1 is to, this will become 1 is to 0.703 is to 1.1. So that is the ratio of D00, D110, and D111. So this procedure may also be followed for other crystal system also, and we'll get different values corresponding to this interplanar distance. For simple cubic, it will be 1 by D100, that is 1, that is first plane, and then 1 by D110, that will be root 2, value will be root 2, and in the last case that is 1 by D11, if you consider, then that is root 3. That ratio I'm saying. So if you take that values that we just calculate, that will be like this. And then if you consider body centered cubic, that is BCC, then this ratio will be 1 is to 1 is to, this is to, okay, if you take that ratios. So 1 is to, then this will be 1 by root 2, then this will be root 3. Then we have the FCC, which is also having 1 is to root 2 is to root 3 by 2. Okay, so in this way you can find out for the different kind of crystal structure also by using the X-ray spectrometer. So that is the method. So this table, from this table you will be getting ratios between interplanar distances, and if you are having an unknown sample, unknown crystal, and if you study the X-ray spectrometer, and if you get this kind of ratio, then you can say this is PCC, this is FCC, or this is simple cubic, something like that. Okay, let me calculate that value. As you know, this is okay. We are getting 1 is to 1 by root 2 is to 2 by, I think it is 2 by root 3, right? 2 by root 3. Okay, so that is FCC. Whatever we are calculated, that is FCC, right? So that is FCC. But because we are getting D100, what we are getting? D100, we are getting 1. Then we are getting 0.704, 703. So this is like, if you calculate that, that will be 1 is to, then this is 1 by root 2. This is not root 2, this is 1 by root 2, and this is 2 by root 3. Some differentiate. Anyway, so if you are calculating this interplanar distance d11, d100, d110, d11 for these three cases as we discussed here, and then the ratios will be like this. So from that table you can find out whether your crystal is having simple cubic, body centered cubic, or FCC. Okay. Now another method that is used similar to this Bragg's uh, spectrometer, but a very slight change. And in this method, we will be using powder instead of a single crystal. We will be using powdered form. Okay, so the this is called as a powder crystal method. This is called as powder crystal method. So the problem with the single crystal is we cannot get a single crystal exactly perfect, right? Because some kind of uh, defects or some impurities, etc., may be possible, and there can be some kind of mechanical damages also for a crystal. So a single crystal with a perfect shape, okay, without any damage, that is difficult to get such kind of a crystal. That is difficult. If you are getting such a crystal, then only you can use that single crystal in Bragg's reflection. But in this case, what we are doing, we are using powder crystal. Okay, so we are actually making the powder of those crystals. Okay, and in this case, if you consider the Laws and the Bragg's technique for investigation of crystal structure, that can be applied only if a single crystal of reasonable size and without any damage is available. Okay, that is in that case only we can use that technique. But in general, a large crystal without fault or without any defect or without any impurity, that is difficult to find. Okay, then we consider another method, and this is from Diffraction. This method is from that this is Diffraction. This method is from that Diffraction, and here we will be using powder form. Okay, so the specimen was taken in the form of a well powdered sample of crystal. So same crystal we will make it as a powdered form, and that in a very thin glass capsule we'll consider. So this is your sample here, and that is in powdered form in a very thin glass capsule. And the all other experimental arrangements are shown here, as you can see from here. A narrow beam of X-ray will be produced by the source, and that will be passed through these slits S1 and S2, that will be collimated, which means it will become narrow, very narrow. This wide, if some radiation, some X-rays are coming in different direction, that will be filtered out. So only that very narrow gap, through that very narrow gap, that X-rays will be coming, which means that they are collimated. Collimated means they are in this in a single line. Okay, very narrow. Okay, and that X-rays will be falling on that powdered specimen at this center, and this the specimen that you can see in this figure is suspended vertically on the axis of the cylindrical camera. So if you look it in three dimension, it will be like a cylindrical structure like this. I will show it below, or in this side I will show. So whatever you are seeing in this figure, this part I am saying. So the part where we are having that sample. So that part, if you consider, so that will be something like this, some kind of a cylindrical shape. Okay, that is some kind of cylindrical shape, and the inside this there will be photographic plate. Okay, photographic plate, and at the center of this we are having that sample, and the X-rays are coming in this direction and hitting on that sample, and that after hitting on that powdered sample, that will be reflected as we explained. So here we are having that photographic plate, so this will be reflected in different direction, and that will be captured by those photographic plate. So this will be almost 180 degree we will be having that photographic plate. Okay, in 180 degree we will be having, and whatever reflection which is coming after that, that will be recorded. So that is method. So the powder specimen of the crystal can be considered as a collection of random oriented tiny crystals. Okay, because it is the same crystal in powdered form, so we can consider that as a large number of small crystals, very tiny crystals together. That is the powdered form. So if you take any crystal and make it powder, which means that it is same crystal but in a very small size. Okay, each of those small tiny crystals will be reflecting these X-rays in different directions. Okay, for a given wavelength and given value of d, there can be only one value of theta, one value of glazing angle, which satisfies the equation and lambda equal to 2d sine theta. Okay, and such reflected beams emerge out from the specimen in all directions, inclined at an angle to theta. Okay, with the direction of the incident beam. If you consider this as your if you consider this is your incident beam, and with respect to this incident beam, your scattered or the reflected beam will be having angle of 2 theta. That will be having angle of 2 theta. Why? Because millions of tiny crystals in the specimen which are randomly oriented. So then we have to consider this angle 2 theta. Okay, so we are getting, this is your X-ray direction, and after that reflection, that will be somewhere here, and if you take that angle, this has to be 2 theta. Because we are having large number of tiny crystals in there, and all those crystals will be reflecting these X-rays. So they are randomly arranged, and we have to take 2 theta angle. So the reflected X-rays will be on the surface of that cone, and the vertex at the specimen based on the that photographic film, and having a semi-vertical angle 2 theta. Okay, and from this also we can find out what will be the angle, the distance, d value. And if you consider that film, then the film will be something like this. We'll be having a center spot, and we'll be having many other circles, let's say like this. So we'll be having something like this, some kind of figure. You can get this figure. There are many other sources available. You can just check that. On this side, we'll be having something different. So this will be a little narrow as compared to the first one. And from here, they will be having this last. So this kind of a pattern that we'll get, and from that we can find out what is the value of t. So this is the powder method, how we will determine the interplanar distance, and this is proposed by Diffraction. And why it is important? Because we will not get a very large crystal without any imperfection or damage. Okay, in this way you can do it even if it is having some imperfections, it will not be affected because we are crushing it, we are making it powder form, and all those tiny crystals will be reflecting those X-rays, and we are measuring the angle as 2 theta, and we'll get the corresponding uh, parameters.